So, if you want an exhausted elite athlete to jump higher, the absolute worst thing you can do is um, let them rest.
Which sounds totally counterintuitive.
Right, completely. I mean, you'd think that putting a tired athlete on a bench for 10 minutes would, rejuvenate them.
Yeah?
But today we're looking at this physiological paradox where sitting still actively degrades your neuromuscular output.
Yeah, it basically puts the system to sleep.
Exactly. To get maximum explosive flight out of a body that's already drained, you actually have to shock the system. You have to pile on even more physical stress right before they perform.
It creates this really fascinating metabolic traffic jam. Like when an athlete just rests, their nervous system downregulates.
Mm-hmm.
The chemical pathways essentially park their cars on the highway. But a targeted explosive shock clears those lanes. It leaves the biological machinery in this heightened state of sensitivity.
But the margin for error is practically zero.
Oh, absolutely. It's precision neuromuscular engineering.
And that is the core mission of our deep dive today for you listening. We are going to uncover exactly how elite athletes manipulate their neurophysiology to instantly hack their jump height.
Yeah, rewiring their power output on the fly, basically.
Without adding any bulky muscle. And we're drawing from a really specific, dense piece of 2024 research. It's published in the Journal of Sports Science and Medicine.
The data in this one provides just an incredibly sharp look at the invisible machinery of human performance.
To give you absolute scientific clarity on our foundation here, the paper is titled Post-Activation Performance Enhancement of Countermovement Jump After Drop Jump versus Squat Jump Exercises in Elite Rhythmic Gymnasts.
That is quite the title.
It's a mouthful, yeah.
Yep.
And it was authored by Chengbo Yang, Lin Shi, Yanan Liu, Hongli Wu, and Dawei Yu.
But that title really does perfectly map out the mechanism we're taking apart today.
Okay, let's unpack this, starting with that core concept at the front of the title. Post-activation performance enhancement, or PPE. We know this is the phenomenon where basically a voluntary muscle contraction acutely enhances your subsequent performance.
Yeah, but we're not just talking about warming up the tissue here.
No, not at all. Looking at the cellular mechanics, we are talking about fundamentally altering the protein sensitivity within the muscle fiber itself.
Exactly. The primary driver is myosin light chain phosphorylation.
Big words.
Yeah, let me break it down. When an athlete performs that highly intense initial contraction, like a heavy squat calcium, floods into the sarcoplasm of the muscle cell.
Okay.
That calcium binds to calmodulin, which activates a specific kinase. And this process physically alters the structural conformation of the myosin cross-bridge heads.
Wait, it literally moves them.
Yes, it physically moves them closer to the actin filaments.
So for a really brief, highly sensitive window of time, the next neural signal sent from the brain doesn't just cause a normal contraction.
Right.
It results in a much faster, far more forceful cross-bridge cycling. You're basically leaving the biochemical lights on in the muscle cell.
That's a great way to put it.
And this brings us to the really unique test subjects of this study, rhythmic gymnasts. Because, if you're studying extreme power output, you might default to Olympic weightlifters or sprinters.
Sure.
But rhythmic gymnastics presents this highly specific biomechanical dilemma.
Well, the scoring system of the sport demands it.
Mm-hmm.
Judges evaluate leaps based almost entirely on the shapes the athlete holds during the flight phase.
Right. To display a perfect split in midair, you need maximum hang time.
And hang time requires absolute peak vertical velocity right at takeoff.
But unlike a football player, a gymnast can't just go to the gym and put a massive barbell on their back to build huge muscles.
No, they can't.
Because adding physical bulk actively destroys their mechanics. I was looking at the physics of their routines, and if you induce muscular hypertrophy, say, you add an extra couple pounds of muscle to the quads and calves.
You fundamentally alter their moment of inertia.
Exactly. Any mass added further down the leg basically acts like a longer pendulum.
Which exponentially increases their resistance to rotation.
Right, and they need rapid, tight rotational reactivity. If you add heavy biological metal to their chassis, you weigh down the pendulum, they lose that defining lightness of the sport.
So they need the power, but not the bulk.
Yeah, it's like revving a high-performance car engine right before the light turns green.
Yeah.
You're priming the neuromuscular system for explosive power without modifying the chassis.
If we connect this to the bigger picture,
Hmm.
finding ways to increase power output acutely, like in the exact moment of competition, without causing chronic hypertrophy, that is the absolute holy grail of sports conditioning for bodyweight-dependent athletes.
You want the central nervous system firing with maximum ferocity, but the mass of the engine block stays completely unchanged,
Precisely.
which sets up the sheer difficulty of the trial these researchers built. They recruited 20 elite female rhythmic gymnasts using a randomized crossover design. But what really caught my eye was the biological state these women were in before the test even started.
Oh, this is the best part.
Right. They didn't test them fully rested. They tested them smack in the middle of their standard training block.
And that standard block is grilling. 12 sessions a week. 6 days a week, 4 to 6 hours per session.
Wow.
Yeah, that is up to 36 hours of elite-level training weekly. The baseline fatigue in their systems is massive.
But testing under those conditions makes the data so highly applicable to actual competition, because no one is ever perfectly fresh.
Exactly.
So under that crushing cloud of fatigue, they tested 3 different conditions over 3 separate days to see what would boost their jump height.
Okay, let's hear.
Condition 1. 6 drop jumps, dropping off a 50.5 centimeter box. Condition 2, 6 squat jumps utilizing the optimal power load.
Right.
And condition 3, a control condition where they basically just sat still.
We should definitely break down the biomechanics of that optimal power load, or OPL.
Yeah, what is that exactly?
Because it's crucial to the squat jump condition. The researchers didn't just throw a standard 20-kilo bar on their backs. They actually mapped each individual's force velocity curve.
Okay.
In physics, you can't maximize force and velocity at the same time. As weight goes up, speed goes down. So OPL finds the exact mathematical intersection where the wattage output peaks.
Oh, that makes sense. And for this group, that intersection averaged out to 6.9 watts per kilogram of body weight.
Yeah.
So generally between 30 and 70% of their max back squat.
It is a highly demanding mechanical movement.
It is. But looking at that control condition, the sitting still... Wait, if these athletes are already training up to 36 hours a week, wouldn't doing nothing be the best way to prep for a big jump? Why tire yourself out more?
You'd think so, but the data showed the exact opposite.
Really?
Yeah, when they sat in the control condition, their jump height actually decreased by 0.35 centimeters at the 9-minute mark.
Oh, wow.
Sitting still caused their baseline fatigue to just fully set in. It proves that a targeted neuromuscular stimulus is strictly necessary to overcome that exhaustion.
So rest actively hurts them.
Yeah, the downregulation of the nervous system is part of it.
Yeah.
But you also lose muscle tendon stiffness. When you sit still, your core body temp drops slightly, and that tissue loses its optimal stiffness. It basically becomes slack.
And a slack tendon can't rapidly transmit force from the muscle to the bone.
Exactly. It absorbs the energy instead of projecting it into the floor.
So sitting still lets the biological slack set in. To beat that, you need the shock. So let's look at the active jumps. But the success wasn't just if they worked, it was the timeline of when they worked.
Right, the time course of potentiation. This is where cellular mechanics meet metabolic fatigue.
Let's trace the drop jumps first. This was the immediate spike. They stepped off the half-meter box, landed, and rebounded instantly. And at exactly 30 seconds post-exercise, their jump height increased by 0.8 centimeters.
It was practically instantaneous.
Yeah. Why so fast?
Well, a drop jump involves an incredibly fast stretch-shortening cycle. The athlete hits the ground and is back in the air in under 250 milliseconds.
That's quick.
Very. And during that landing, the muscle spindles detect a violent stretch. This triggers a spinal reflex that instantly recruits your highest threshold motor units, specifically the type 2 fast twitch fibers.
And because it happens in a fraction of a second, relying on the elastic energy in the tendons, it doesn't require a huge supply of ATP.
Exactly. The mechanical work is so brief, it bypasses the massive accumulation of hydrogen ions and inorganic phosphate.
Which is what normally causes muscle fatigue.
Right. You get the massive potentiation without paying the heavy metabolic tax.
The fatigue is low, so the potentiation shines through immediately for that 30-second spike. But the squat jump data paints a totally different timeline. They use that heavy optimal power load. The cycle is vastly slower, and initially, right after those 6 jumps, their vertical actually tanked. They got worse.
Yeah, they were worse off at first.
But then, at exactly 9 minutes post-exercise, this delayed spike occurred. It pushed their jumps 1.02 centimeters higher than baseline.
What's fascinating here is the two-factor theory playing out in real time.
How so?
Fitness and fatigue operate simultaneously. Moving that heavy load generates a huge software upgrade to the nervous system, massive potentiation. But it also generates massive acute metabolic fatigue.
Ah, the biological traffic jam.
Exactly. At minute 1 or 3, The muscle fibers are primed, but they're bogged down by the acidic environment from the exercise.
So the fatigue completely masks the potentiation.
Right. But the crucial reality is that fatigue dissipates much faster than potentiation does. By minute 9, the fatigue falls away, leaving that massive underlying potentiation fully exposed.
To translate this directly to your world listening to this, because this rule applies whether you're on a gymnastics mat or waiting to give a big presentation timing, your warm-up depends entirely on when you need to perform.
Absolutely.
If you need immediate explosive power, like within 30 seconds, use a rapid elastic movement like a drop jump.
You avoid the metabolic tax.
But if you know you have a 10-minute wait before your event, doing a heavier loaded squat jump pays off better later. You purposely incur the fatigue, knowing you have the runway to let it clear.
It transforms warming up into scheduling your peak biological output down to the minute.
It's incredible. But digging deeper into the data, this hack doesn't apply uniformly to everyone.
No, it doesn't.
The researchers mapped the inter-individual variability, and the dividing line between athletes who saw massive gains and those who saw minimal improvement was entirely correlated to their baseline strength.
And the statistical evidence here is incredibly robust. They track the athletes' relative back squat 1-rep maxes.
Their strength relative to body weight.
Right. The positive correlations were stark. The Accorda value for the drop jump response was 0.63, and for the squat jump, it was 0.64.
And in exercise science, an R value above 0.6 indicates a really strong positive correlation.
It does.
It proves that the stronger the athlete is at baseline, the higher the peak PP response they can achieve. I like to think of it like a slingshot.
Okay, a slingshot.
Utilizing PP during the jump is the action of pulling back the band to load it with energy.
And your baseline strength represents the thickness and quality of the band itself.
Exactly. If your internal biological band is weak, no amount of perfectly timed metabolic hacking is going to give you maximum distance.
You just can't pull a thin band back far enough.
Right.
The biological reason that band is thicker in stronger athletes points directly back to muscle fiber composition. Stronger individuals naturally possess a higher percentage of type 2 fast-twitch fibers.
Which are the fibers responsible for rapid, forceful contractions.
And crucially, those are the specific fibers that are highly responsive to that post-activation potentiation we talked about.
So a weaker athlete just structurally lacks the hardware to install the software update.
Essentially, yes, the potentiation is structurally bottlenecked.
Which means there are no biological shortcuts. To effectively use these power hacks in competition, athletes still have to do the grueling, unglamorous strength work in the off-season.
You have to build the dense fiber architecture months in advance, just so you have the capacity to exploit a 9-minute metabolic window later on.
It's all connected. Okay, let's pull these complex threads together for you listening. Let's synthesize the core findings.
Sound good?
First, if you're carrying compounding fatigue, resting passively before an explosive event downregulates your nervous system. You must deliver a targeted stimulus.
Second, the type of stimulus dictates your timeline. For a quick 30-second vertical power boost, the drop jump is the optimal tool.
Third, if you have a 9-minute runway, using the optimal power load in a squat jump gives you a deeper, delayed boost.
And finally, baseline strength is the non-negotiable foundation for all of this.
It really reframes how we view human output. For you listening, if you want to explore the dense cellular mechanics we touched on today, I strongly encourage you to seek out and read the full article in the Journal of Sports Science and Medicine.
It's a fantastic paper.
It really is. And while you're doing that, make sure to follow the channel and turn on your notifications so you never miss our deep dives into this level of science-backed performance data.
The literature on human limits is constantly evolving. These studies are where the real breakthroughs happen.
Definitely. Which leaves me with a final lingering thought for you to explore on your own today. We spent this whole deep dive analyzing how these gymnasts manipulated their nervous systems to push their jumps up by a full centimeter or more. But remember the baseline condition of these athletes. They executed these physiological hacks while carrying the crushing fatigue of 36 hours of weekly training.
Their systems were already deeply exhausted.
Right. So what does that say about the true biological ceiling of human power output?
Oh, wow.
If we could perfectly isolate a rested neuromuscular system, strip away that fatigue entirely, and perfectly time these stimuli, are we on the verge of seeing athletes achieve explosive feats that we currently consider physically impossible?
That is a wild thought.
Right, because if they can defy gravity while utterly exhausted, just imagine the physics of what happens when the human machine is truly